Okay, let's now compute an example. I took the thing presented earlier and just tried to clean it up a little bit so that we can use it as a reference. So let's consider the vector field. Whoops. Consider the vector field, capital F arrow, because I don't want to bold the capital F. Again, please be very vigilant and clear about what's a vector versus what's a scalar. Okay, so the vector field I have in mind is angle bracket x over y, comma x cubed. And suppose, so there's a vector field part. Now the curve C has to be defined completely independently, so the vector field doesn't have to relate to the curve C and vice versa. They're just two separate things that need to be provided. So, and suppose that C is, and we'll draw a picture. Okay. Here the direction of parameterization matters for these things. And so we'll have here -2 on the y-axis, +2 on the y-axis, and we've got a thingy that looks like that. Okay, so then we'll find, based on this, we'll find the integral over c of f dot dr. Don't forget the arrow on the f and the f on the and the arrow on the r in the dr. So to formulate our answer to this question, we are going to need to create a parameterization. Yeah, we're going to write that parameterization in the form of a vector function, though. So c as a vector function has vector function. It's really parameterization. Remember, vector functions and parameterizations are, while they're technically different, they're morally the same. It's just the information is organized to look different. The same information is just repackaged. So r of t equals, how about we keep the x stuff as usual, 2 cosine of t, but due to the fact that you have a flipping of direction, here let's just negate y and have -2 sine of t with so from pi over 2 to 3 pi over 2, and the flip will make it all work out. So pi over 2, yeah, to less than or equal to t less than or equal to 3 pi over 2. And we'll just comment here that this right there, 2 cosine of t, is going to be, that's our x of t. And then this part right there, -2 sine of t, that's our y of t. Okay, so there's our parameterization of the curve written as a vector function. And we have taken into account the direction. So now let's work out, just because it's an ingredient we need, let's work out f of r of t, which is really, it's not good notation, but all the books do it. It's really shorthand notation for this. So let's just write it out, right? So f of r of t, it's what this is really meaning is f of x of t comma y of t. And so let's just fill those in. Yeah, so in our example, it's f of, well, x of t gets replaced with 2 cosine of t. And then comma, now y of t, well, y of t, we have it right here, was -2 sine of t. So -2 sine of t. Well, and then when we plug in 2 cosine of t as well as -2 sine of t for x and for y in this over there, right, we're just now applying, there's the name of the function, so we're just applying this. We ought to get angle bracket, okay, x over y. So x over y, remember this is x, this is y. So we'll have 2 cosine of t over -2 sine of t, comma, and then we have x cubed right there. So that's going to be 2 cosine of t quantity cubed. So 2 cosine of t quantity cubed, close angle bracket. So that's this part. We're also going to need r prime of t. So why don't we just compute r prime of t? It's been a while since we've done this kind of thing, but we literally just take, for a vector function to take its derivative, you just take the derivative of one component at a time. So 2 cosine of t differentiates to -2 sine of t, and then -2 sine of t, let's see, that was unfortunate, differentiates to -2 cosine of t. Okay, now let's piece everything together. Okay, so we were asked to find the integral over c of f dot dr. How you do that, though, is you set up this. And we've done really most of the work. We just need to actually plug in the pieces. So integral from a to b, in our case pi over 2 to 3 pi over 2. Yeah, that was taken from right over here. Okay, then we have this f of r of t, which is really actually technically this, and we worked it off to the side here just so that we didn't have to do too much all at once. If you want to reorganize the order of steps later, fine. I just wanted to get some of the ingredients in place because this is new to us. Yeah, so we take this vector and just really copy this over here. So angle bracket 2 cosine of t over negative 2 sine of t, comma 2 cosine of t, quantity cubed, close angle bracket. Cool, that's this part. Now we need to write the dot. That's right there. Yeah, so we'll just write dot as in dot product. Then we have r prime of t. We worked that out. So let's just copy this right over here and have angle bracket negative 2 sine of t, comma negative 2 cosine of t. Close angle bracket. So now we've written r prime of t. Now literally all we do is write dt. There we go. This integral is not one that we could pass off to a student in Calc 1. Not quite yet, right? But we're so close. We're so close to being able to pass this integral off to somebody in Calc 1. So integral pi over 2 to 3 pi over 2. All we really have to do is perform the dot product. So this times that, you know what? The negative 2 sine of t's cancel out. So we're left with, actually, 2 cosine of t. Okay, and then plus, now we have 2 cosine of t quantity cubed, right? Times negative 2 cosine of t. So we're actually going to be left with a minus. Let's just turn that into a minus then. 2 times 2 times 2, or 2 cubed, and then times another 2. So 16. Yeah, 2 to the 4th. 16 cosine to the 4th t. And then all that, technically in parentheses, dt. Cool. This is not a particularly easy integral to do, but it is, at least it looks like a Calc 1 style integral, and so we will end it there. We'll just say we've set up enough of this. Let's take a look at some more examples.